right, so this is the last lecture of week 3. This is the fourth one. We're going to continue to talk about semiconductors and get into an actual application of them and how we're finally going to be able to control how electrons move around in metals and nonmetals and that kind of thing. So let us begin. Doping semiconductors. So semiconductors in general, we talked about this, the generic semiconductor, where's my thing, right, has a filled valence band. Let's pretend that this is filled, right? So this is your normal semiconductor, right? Has a filled valence band, an empty conduction band, right? And it has this band gap between the two. We know that in general, electrons don't move. Electrons only move if they are in the conduction band. Right? And so a normal semiconductor just sitting there with no electrical energy applied to it is not going to have electrons moving around in it, right? We can control the flow of electrons because we know how big that band gap is, right? So we have the filled valence band, we have our band gap. These are not metals, these are not insulators, and so we can kind of control how this is. Depending on what elements we use to create that band gap, we can control how big the band gap is and how likely it is that they will be conducting. Right? Another way that we can control this is through doping, right? And so doping is adding very small amounts of an impurity. This is doping. Affects the conductivity. Affects conductivity. Right? So there's two ways that we can do this. One, we can do N-doping or N-type doping, right? Which means adding a group 5 element. So things like phosphorus, nitrogen, arsenic, right? Those kinds of things. If we add those, what we're doing is, remember that we want this full valence band, which is generally 4 electrons per atom. If we do N-type doping, we still have our full valence band. This is still full down here, but now we have just a little bit of these group 5 elements, and what they're going to do is they're going to add just a tiny little layer of electrons to the conduction band, right? So if we have a few more, this is N-doping. If we have a few more electrons already in the conduction band, you can imagine that the electrons in the conduction band move. And so we increase the conductivity quite remarkably by just adding a little bit of this impurity, this phosphorus, nitrogen, or arsenic impurity to a semiconductor, right? We're creating a couple of electrons in that conduction band, and we're allowing those electrons to move around. The opposite is, what if we go the other way, right? What if we add something that has not enough electrons to fill the valence band? That is called p-doping. That is group 3 elements, right? So things like aluminum, gallium, indium, etc. Right? If you add in p-doping, right, then you end up with you have elements in there that don't have enough electrons to fill the valence band, and so instead your valence band, let's see how good at drawing I am, ends up with this kind of thin line of emptiness right at the top, right? So the very highest energy orbitals in your valence band don't ever get filled. This is p-doping. And so what the result of this is that actually electrons now still move, but they move to fill the holes in the valence band. And so actually either way we go, if we add, if we do p doping or if we do n doping, we create this movement of electrons. So either way we increase the conductivity. So both p doping and n doping both increase conductivity. Okay? So if we have a very pure semiconductor, like a just pure silicon semiconductor, we have this kind of the first case, the normal semiconductor, where we have a full valence band, we have an empty conduction band, and with the application of energy, we can create electrical current because that conduction band is there to allow the electrons to move around. With n doping or p doping, we're creating things that already have ways for electrons to move around, and so this can be really useful too. One of the ways that this is very useful is in light emitting diodes. And what we do with light emitting diodes is we put a p doped semiconductor next to an n doped semiconductor. Right. So I always think of n for negative. So n means that there's more negative charge than there was than the normal case. And so that means that there's more electrons. So n-doped means that we have a little bit of electrons in the conduction band, right? P-doped, P is for positive, and so there's more positive charge, which means we have fewer electrons than we would normally have. And so we have these holes there. Right? So what a light emitting diode does is it puts a p-doped and an n-doped semiconductor in contact with each other. And what happens is in the middle here, they kind of neutralize each other out. So there's not really any way for them, for the electrons in this conduction band here to see the valence band or conduction band there. But what we do is we apply a voltage across this thing. I'm going to mess up my notation, I know, because it's been a long time since I took physics. So if this is wrong, I apologize. But we apply a voltage across this thing, and what this does is applied voltage gives those electrons in the conduction band, pushes electrons into the junction between them. Oh, I've lost my cursor here, hang on. Into the junction. I guess I didn't label the junction, but the junction is here. That's that middle part. Right? Pushes electrons into the junction, and then they fall into the valence band of the p-doped semiconductor. Okay, so electrons go flying around the circuit, right? So we have apply a voltage, so we end up with electrons moving around the circuit. The electrons come in here, we add energy to it, and that means that on the other side, these electrons come out and they go from the n-doped side, the conduction band on this side, down into the valence band of the p-doped semiconductor. This drop in energy, right, with this going from up here to going from up in the conduction band to down in the valence band, the drop in energy of those electrons is emitted as light. Right? And so how do we know what kind of light we get out? This depends on how big the band gap is. So the size of the band gap relates to the wavelength of light. That's emitted. And so if we measure, if we get the band gap exactly right, we can say that the wavelength of light that's emitted comes from Planck's constant times the speed of light divided by the energy of the band gap, right? So here's our band gap energy. This is H is Planck's constant, C is the speed of light, and this is the wavelength of light emitted. Right? So this is wavelength. So if we can control the band gap of our semiconductors, we can control what type of light gets emitted. And so depending on which types of atoms you use and elements you use in your semiconductor, you can actually get green light, blue light, red light. And so all these LEDs that create these different colors and such, the reason that or the way that they're doing that is because somebody somewhere figured out the correct band gap to match up with that particular wavelength of light. So that's semiconductors. That's an application of semiconductors to make LEDs and all that kind of stuff. Um, that pretty much does it for week 3 content. If you have questions or concerns, definitely go through the usual channels on D2L, office hours, all of those other things. Please let me know if there are things that don't make sense. I'm happy to sit with you and try to work this stuff out. Thanks, and I'll see you again next week.